Hi guys, myself Pranav is here to deliver today's presentation, Power Transformer Part 50. As the subject is of the continuation, so for your information and convenience, the link of the previous one is given under the description box. Let's start here. The zigzag grounding transformer. Application of grounding transformers to ungrounded three-phase system would be of much significant as because their system reliability, short circuit fault current withstand capability, over voltage with basic insulation levels, etc. must have to depend on the characteristics of neutral grounding arrangement. Mainly for delta connected or ungrounded power systems, the usual provision of zigzag transformer that can be connected as a high impedance ground system. Implementing zigzag transformer as of a high impedance ground system would have been the least costly method compared to Scott connected transformers. To connect with power system, the zigzag transformer has the basic purpose of providing a neutral point for grounding purpose, which helps to create an easy path to the ground fault current during line to ground fault. Apart from the working provision of neutral for grounding, a zigzag connection can also be suitably applied for supplying single-phase line to neutral loads when working with a three-wire ungrounded power system. A zigzag transformer is more effective for grounding purposes as because configurationally its winding composition is such that it has to provide less internal winding impedances going to the ground than that of when using a star connected transformer. Zigzag transformer with a schematic diagram as shown in figure 162, we can compile that number one, zigzag transformer has no secondary winding and is composed of a magnetic core with having 3 columns. In each column, there are 2 equal windings per phase. Number 3, each coil is configured with the same number of winding turns, that is of turns ratio 1:1, but coils in each limb that would have to wound in opposite directions. So, the transformer would have to contain 6 coils on 3 core limbs. The first coil on each core is connected contrawise to the second coil on the next core. The second coils are then all tied together to form the neutral, and the phases are connected to the primary coils. The direction of current in the 2 windings on each limb is opposite to each other. See the schematic diagram. coil connections as follows. That is, phase of the outer coil connected to phase of the inner coil. A1A to C1, C2N neutral. B1B connected to A2N. C1C connected to B2N. That is, N is the neutral. Whenever currents in the terminals A, B, C having with equal in magnitude and phase are thus to be applied, then the underneath happenings would have to entertain due to zigzag connections. 1. The ampere turns of the A2N winding would have to cancel the ampere turns of the B1B winding. The ampere turns of the B2N winding would have to cancel the ampere turns of the C1C winding. The ampere turns of the C2N winding would have to cancel the ampere turns of the A1A winding. If currents that are applied in terminals A, B, C of equal in magnitude but 120 out of phase with each other, then the corresponding ampere turns in the windings that cannot be cancelled out, but the transformer that would have to restrict the flow of current to a negligible level of magnetizing current. It is therefore to be concluded that the zigzag winding would have to provide an easy path for in-phase currents, but does not allow the flow of currents that are 120 out of phase with each other. As the formation of neutral through zigzag connections is much more stable, so a zigzag transformer is thus to provide a perfect grounding applications on delta connected systems, that is an ungrounded three-phase systems. Under normal system operation, the voltage applied to each phase of the zigzag transformer is balanced and the magnetic flux of outer and inner coil windings will cancel each other, while any fault would have to occur between phase to earth, then the voltage applied to each phase of the zigzag transformer is no longer in balance. Hence, fluxes in the windings would never be cancelled out. Any occurrence of single line to ground fault, then in the faulted phase, the magnetic flux in the zigzag transformer coils would not be equal. As of the consequence, there will be a flow of zero sequence current, that is I0, through all the windings of the zigzag transformer, and at its neutral, these currents are being added up, that is 3I0. The zero sequence impedance of the zigzag transformer can have to contribute to limit the single line to ground fault current. If a zero sequence impedance is imposed, then the power and the corresponding leakage impedance rating of the transformer may have to be calculated while in designing. Again, I repeat, if a zero sequence impedance is imposed, then the power and the corresponding leakage impedance rating of the transformer may have to be calculated while in designing. So far, the zigzag transformer is concerned, other than zero sequence, that is earth fault current, to exist between the transformer's neutral to the faulty phase, there would have been little impact on positive and negative sequence currents. In an ungrounded power system, a zigzag transformer with the neutral connected to ground has to provide a stable path for zero sequence currents resulting from line to ground faults. However, two types of three-phase grounding transformers are normally used to provide neutral connection point on a delta fed system. One, a zigzag connected winding with or without secondary winding. Number two, a start delta, that is YND, connected winding with a delta connected secondary that may or may not be employed to supply auxiliary power, as in figure 163. See the diagram. Start delta grounding transformer with flow of fault current. In both cases, while connected to three-phase lines, then under normal conditions, the rated voltage is balanced with the phase shifted by 120 degree, and only the excitation current required for the grounding transformer that circulates through the windings. Excitation current is the vectorial sum of magnetization current and core loss current of the grounding transformer. Excitation current is the vectorial sum of the magnetization current and core loss current of the grounding transformer. Through Fourier analysis of the excitation current waveform, it can be revealed that substantial amount of third harmonics are present in that current waveform. It has been exhibited that the third harmonic component is created almost entirely due to the magnetization current, followed by a very little percentage as due to the core loss current. That is, magnetization current is the most vulnerable in case of for creating third harmonic components. The triplet harmonics have zero sequence in nature and are being accumulated as neutral current. While the delta fed system that would have linear loads, then the neutral of the connecting grounding transformer may only have to carry the current as due to imbalance between the phases. But if the connected loads are of nonlinear type, then that would produce third order harmonics which are in phase on all the supply phases. Consequently, the third order harmonic currents that would thus to add in the neutral of the connecting grounding transformer. Zero sequence currents, therefore, would have to begin with one, unbalanced loads, and fault current involves to ground. typical characteristics of ungrounded transmission system. The designers have the opinion that an ungrounded system would provide higher system reliability than would have a grounded system, since then a ground would not have to create a fault. Again, I repeat, the designers have the opinion that an ungrounded system would provide higher system reliability than would have a grounded system. Since then, a ground would not have to create a fault. As a matter of fact, that technically accepted ungrounded power systems are very much common in industrial plants worldwide, because the system would have to allow uninterrupted operational sequence even at the presence of single line to ground fault. In an ungrounded system, even if current carrying conductor is not to be intentionally grounded, but current still flows from any or all phase conductors to ground. How it is possible? This will happen as due to existence of natural capacitance of the system phase to ground. See the diagram. Distributed natural capacitances between phases and distributed natural capacitance between phases to ground. Particularly on a three-phase, three-wire HV system, though there will be no direct ground fault current, but there may still exist charging currents through the ground leakage capacitances. However, the fault current level is significantly low and perhaps no need to take extra protection. As of figure 164, the power system which has no intentional ground, so only zero sequence current I0 would have to exist in the system. In power systems, even under healthy conditions, there may have zero sequence current as due to the difference between the phase to ground capacitance of the phases, that is CAG or CBG or CG, and the loads as connected phase to phase. Once there would have a single line to ground fault on the power system, then the phase to ground voltage of the faulty phase must have to collapse. That is, as of figure 165, VAG equals to 0. Consequently, the phase to ground voltages of the remaining unfaulted phases would thus to be increased by a factor of √3 and have to shift by 60 degrees. When fault occurs on the system, the high impedance of the phase to ground characteristics, phase to ground capacitance of all the non-affected feeders in the system limits the fault current to some extent. Again, I repeat, when fault occurs on the system, the high impedance of the phase to ground capacitance of all the non-affected feeders in the system limits the fault current to some extent. The magnitude of the voltage collapse that would have to depend on the magnitude of the fault impedance. Basically, the magnitude of the voltage collapse would have been higher if there is smaller in magnitude of the fault impedance. The zero sequence current I0 as produced would have to lag the zero sequence voltage V0 by 90 degree as of figure 165. In an ungrounded power system, it is rather to be recommended to provide higher sensitivity flux summation CT, that is current transformer, to have an accurate measurement of the zero sequence or residual current during a single line to ground fault. In an ungrounded system, that must have to design with the basic perception of considering line to line voltage insulation. Now, see the diagram at no fault situation, that is voltage phasor diagram showing the phasor relationship between the phase to ground voltages and phase to phase voltages for an ungrounded power system. This one, while at phase A to ground fault, voltage phasor diagram showing the phasor relationship between the phase voltages, zero sequence voltage, and current for an ungrounded power system. Now the same another drawing, that is phase to ground fault on an ungrounded transmission system. There is distributed natural capacitance between phases, and this is distributed natural capacitances between phases to ground. During the fault, the voltage across the capacitance reduces to 0 in the faulted phase. Composition of vectors as of line to ground fault on an ungrounded transmission system, where IB leads to VBA by 90 degree, IC leads to VCA by 90 degree, and IA equals to minus IB minus IC. Let's stop here. Further to be continued at later stage. Thank you for listening the video. Kindly do like, share, and subscribe. Your subscription would encourage to post more videos. Also share your comments or feedbacks inside the dedicated comment section. If you have any suggestion or specific topic you want, then let me know in the comment section, please. Thank you. Thank you for patient hearing.